come here to reunite many of you after 3 years of almost like no travel. And thanks the organizer for the invitation and for putting together this great event to in honor of Gay, our friends from decades. So the topic I'm going to talk about maybe not sort of like directly related to many of yours talk, but it's something that many of my colleagues that worked on for 20 plus years. So the title looks probably familiar to many of you, and you will see many slides also similar, but I'm indeed including something very recent. The reason is really, if you look at what we're trying to make the models predictive, relevant to biology, in a sense that to expand the data, to really test hypotheses, and all these require mechanistic models. And initially, we want to keep the model as simple as possible. The reason that we have a science in such kind of advanced sort of a stage is because I think the physics has many good laws, and those laws really define each mechanism in terms of minimum parameters, minimum equations. And so I think this is something the scientists in life science in particular also want to be able to emulate, but as we are going to see, it's not going to be easy. And then we mentioned that actually in the next slide. And I will get to more other stuff later on. Oh, I cannot get to work. No, just
it was something like if the pointer had to be try again.
I mean, what was I unable to do?
Yesterday the pointer had to be removed from this. Ah, yeah, now it's working.
Oh, good. Okay, went too far. Okay. Oh, no. Opposite one. Okay, they have. Maybe I don't have to talk. Just go like this. Okay. The problem now you already see what I'm going to talk. Okay. So I want to say that the reason that biology is complicated is because the cell really made of many elements in sort of some proportion. In physics, usually it's just one component, force or energy. They can be converted. If you know the force, you know the acceleration, and then you know the speed, you know the position, you can go backwards and forward. So it's like you have one, you just add, you get two, you get three, you get four. In biology, you have multiple dimensions. You have a 0, 1, we can already create the virtual world. And in biology, actually, it's a lot more. Even for human, if you think the elements we need, of course, the most is hydrogen, and the least is cobalt, that also used in many batteries. And then if you look at think our body is really a collection of molecules. Our human molecules will take this form. And then you can see this is really in this kind of proportion. So that's why we need to be careful to also mindful to take on, to make sure our input, including all these elements. And so that's sort of like more or less in a sense of what we call stoichiometry. If we remember the chemistry we learned in high school, that's really what we really hard at work to balance the equations. And then our body trying to do that too, to keep our cell healthy. And so if you think of population dynamic, because this is really more or less on ecology models, there's really, if you look at the equation, the rate of change is what we call is growth rate. And that's really the birth rate minus death rate. Death rate is something that most of us will be happy to ignore or put as a linear equation, because linear death, because it's too complicated. There's thousands of ways to die. But really there's only one way to grow, the cell multiply, or divide. The cell division, the reason the cell can divide is because there's translation sort of a stage that really produce enough protein to allow the division. And of course, preceding that is the transcription, but the translation takes a lot longer. And then in order to analyze what defines the growth rate, My colleagues 20 plus years ago had this hypothesis, and this really defines this book. The book has become a classic, instant classic. If you have a chance to read that, it's really one of the best written book in ecology and evolution, and in terms of also the growth rate. So this is something we continue to work on. In fact, we are still in our third year of a big grant to trying to test when the growth rate hypothesis will be fair. I will get to that in a few slides. So what I want to highlight is, what really make sort of the growth rate different is because the ribosome content, because that's the machinery to generate the protein. And then the ribosome production, of course, also depend on the protein producer. Ribosome, this is the transcription phase. Altogether, you really can argue that it depends on many things, and the food quality to be sort of put in a very easy to understand context is really you want to have your food resource in the right proportion. Say if you have just eat ice cream, and ice cream maybe not too bad, just sugar, you are not going to grow because it doesn't have a protein, doesn't have nitrogen, and then also not for phosphorus. And then, of course, for community, for population growth, you probably have other things to worry about. The conversion efficiency, the competitions, and also whether or not the nutrient will be recycled. And this is a really big issue for many things. I mean, including if we think about climate change, if we really bury all the carbons, we may, at some time, maybe we get short of carbon. So, but that's not something probably another big issue for now. So this is something we really concerned in the last 20, now almost 25 years, the growth rate. We have growth rate hypothesis. We're trying to see whether or not we can have a growth rate law. Hypothesis, we know we don't know the boundary, so it's just hypothesis. Law is that we're trying to draw the boundary where this growth rate will be true. The last 2 years, we've been really working hard on that and realizing that it's far from law. What our we call hypothesis is really only work for very, very limited range. So when you sort of talk about the growth rate in biology, in ecological setting, one thing that the ecologists do is to put them the growth of some organism in a chemostat. The chemostat, many of you are familiar with that because that's really what I want to spend the next 5 minutes on, because we have a really the true pioneer sitting there. The chemostat is whatever you grow, you can even grow, most likely, the biologists or bioengineers I work with grow algae, grow E. coli, also grow Daphnia. It all can be put in this context. So if you put enough nutrient, and then the flow rate in and out is the same. So after a while, can be a long time, and then we'll be at a steady state. So therefore, this balance out. So you can say, oh, the growth rate is equal to the flow rate. But that's really a gross misinterpretation, because that's really production rate in that sense, because you can change the flow rate. So meaning that growth rate can change, because the really growth rate depends also on the nutrient density, the organism density, and many other things. So it's really make it very difficult. So it's a variable that depends on many things, but also the density itself. So that make it very problematic. But anyway, that's what really biologists will tell you. Okay, you want to know the growth rate? I put a chemostat, and then you can see at the steady state chemostat growth rate of population cells equal to the dilution rate. And for that reason, so chemostat has been really a true amazing instrument that to connect mathematics to biology. And many of our good friends, my colleague Hal Smith, Paul Waldman, wrote a book in 1995. Unfortunately, we're not able to see Paul anymore. Hal Smith retired 2 years ago. The book is 1995. It's also an instant classic. But I want to point out that really the classic one, really in a book form, is a gas thesis. This is a truly classical PhD thesis, and talk about the analysis of mathematical models related to the chemostat. Of course, he also did many more substantial work in this area. I don't have time to talk about this, but because this slide bring up Jeff Butler, so this really I want to say a few minutes about the Jeff too, because Jeff is the one that brought me into mass biology, and through this paper. This is a paper that I think it's one of the truly amazing paper because you can learn so much, not just the mathematics, but also the way how mathematics presented. For instance, the proof of global stability using the divergence criterion was first done in this paper, and then I was happy to be able to emulate that in this paper. And this, I'm sorry. So this paper is, of course, was published in '83. So Jeff was very happy to ask me to read that, and I supposed to report back to him. And I remember in 1985, that's the first time I met Gaia by the in the hospital, and I still remember vividly. You stand by the door, and Jeff laying on the bed. And then on another occasion, I also visited him again with Herbert. We went down, fetch the diet cocoa, but with probably 80% of water. Anyway, by the time I came back 3 months later, he already passed away. Butler is a true genius in mathematics and mathematical biology. Really, his work is always set the standard, and also, I mean, very hard for us to achieve. Anyway, if you have time, I wish you can give it another look of the paper, because the reason I say that is it's not very well cited. It's only 150 some kind of a citation, and our paper far less in terms of significance than his has actually received far more. But this is another story. The citation became probably problematic in terms of measure the significance of work. So I just want to say that I was very fortunate that even before Jeff's passing, Herb volunteered to be co-advisor. So it was easy for me to transition from Jeff to Herb Friedman. So if Jeff lived a few years longer, I also will be the least. So that's why I always view Gaia as my elder sister in mathematics. Anyway, so that's sort of like the side remarks for this occasion. So back to the Chemostat. So I want to highlight that really those people who had chance to work on Chemostat, you will find that the quality of nutrient, the proportion of what you put in the growth medium really will change the growth rate. So the growth rate is highly dependent on the composition. And then the right composition, meaning good quality, that most mimic to the cell demand, will have the highest conversion rate. So that really impact the growth rate. So I just want you to keep this in mind. And this is really what we, even the recent, this was published just 2 months ago, 2 months ago, even though we finished this more than a year ago. This is I don't know how, I mean, this is a good journal, but the time to publish became just way too long. Used to be 6 months, now exact 12 months. We submit on 5th of July last year. It get published on 5th of July this year. It's a paper we were able to, based on our model on our set of Chemostat by a group of people in Princeton. They really try to understand the limitation of a specific element on the growth rate of Ecology. And that's the easiest sort of thing to study in terms of cell, because Ecology can divide very fast as 20 minutes. Most of our cells in our body will take a few hours or a few days or a few weeks. And that they were able to limit like carbon, nitrogen, phosphorus one at a time. And they find that each limitation will have different impact on the growth rate. And that's very interesting, because a mathematician typically trying to think there's a universal formula for the limitation. So that turns out to be even, I mean, challenging for just one limitation. And then in reality, many of these nutrients are limiting at the same time. It's just there's one most limiting, the other one less so. So these are the questions we're trying to formulate some formulas and then provide a range when such kind of formula will actually work reasonably good. And I think we're getting close to that, but then we also know that the range is really small, and then there's a lot more work to do. So here we have a general formula for this translational stage. So we really focus on the translational one because that's really where the lens is uncontrollable. It highly depends on the limitation. It's a paper that's probably the first mathematical model that written by a mathematician on this translational phase, the growth rate. And then the most of these authors biologists, ecologists. So we were ambitious 3 years ago about the project, but turns out to be, the COVID-19 slowed down a lot in terms of data collection. So we end up only used the first year data, not even in this paper, but then more or less I did a meta-analysis with other people's data and then realized that we, even among ourselves, cannot agree on growth rate definition. This is very bizarre because everyone have the well-defined, understood growth rate for that specific organism. But then we still agree that at least for cell level, we want to say these things. And this is just probably going to publish in a week or so because I accepted 2 weeks ago in Ecology letter. It also took a long time, several revision process, but something that we talk about what's been done and what we need to do in the future. I don't have time to really talk too much because it's already 20 minutes. So I have 30 minutes. I want to now talk about the old slides that I prepared. I gave probably more than a dozen times in major meetings. The reason I want to say that is because I really think if you want to get sort of not just respect, get approval from an ecologist, it's probably best to help them to understand the complicated data or the sort of phenomena, and then in the form of a simple model, yet mechanistic, use minimum parameters, and hopefully all these parameters have a clear biological meaning, measurable in the setting. And that's easier than done because really, if you work with biologists who don't know the modeling, they will keep saying, oh, you need to add this, you need to add that. And for me, I'm fortunate to be able to work with people like Chemostat, and now also with mostly work with bioengineers. They know very well about differential equation. They know how difficult to solve it. And so they really also want to understand each term, each equation. But this is really specific. So I think for model, you really have to have a model motivation, model specification, model validation, and then of course, model implications, all these in mind. The motivation was easy. Although I was talking about Chemostat, this is a batch culture. So they grow algae, this time is algae, not E. coli, in a big tank for amazingly up to 3 months. So the good thing is that mathematical model, if it's done well, you can really help them to understand something they cannot explain away. And then just last year we had in-person meeting last June in Montana, and then they know they are confused themselves, so they ask people, this Chemostat experiment, if we do this, what will happen? All the leading biologists, more than half of the time, they predict the wrong result. The experiment result actually is wrong. And all that cases, if they really know the modeling, the Chemostat, if they know as good as any student of gas, they will find out the answer is right there in the simple model and in the simple expression, like what's the yield rate, what's the growth rate in terms of other parameters. So if you change one parameter, will be really increase, not decreasing, will be clear in that setting. But anyway, that's not something I want to explore. Well, actually, we will be working on that in the probably next year on a paper. But this is an experiment that I want to, because it's a really very interesting in its own right. So the 3 set of data you grow algae with low light, probably like this one, you will find that the algae will not grow much because there's not much light. So grow slowly, but then anything grows slow is really nutritious. Because I'm a gardener. I mean, we almost never buy any vegetable anymore because we only use organic stuff. It grows slow, tastes much better. And then these, excuse me, the circles, empty circles, really are what we call like a quality level. So the quality, the higher, the better. Definitely is this line. So because algae at low level, but good quality. So definitely will grow slowly, but surely, I mean, not facing extinction very nicely. And then if you grow at high light, it's not that much higher than, I mean, it's probably what outside. And then you are going to see that the algae will be crazy, just jump. And then, but then the quality quickly drop. And then in this case, somehow the Daphnia can still grow slowly and then control the algae, and then the quality recovers. And then eventually the Daphnia also happy. So this is all sort of also what observed. So what I'm trying to say is that your model should be able to describe such kind of dynamic by changing the one parameter, the light one. And this is highly nonlinear. And so you also want to have a minimum number of parameters. And then finally, there's a threshold around probably like 350, about which the light really is too much. So the algae will grow fast and stay high, because the Daphnia cannot grow fast. Daphnia feeding on algae cannot grow high enough to control the algae to keep the quality, to make sure the quality return to good level. So the quality of the algae really stay low, these empty circles. And then, so you can see that the Daphnia are facing extinction possibility. So that's really just one parameter. You should be able to produce these possibilities. And we know that that's a challenge for a typical predator-prey model, because the predator-prey model really, the logical Vitella one typically just have, here, of course, we don't have algae extinction. The distinction, what we have is the loss of stability of the positive state that usually result in limit cycle, and then limit cycle stays on. You don't have extinction of the predator. Okay? So you don't want to just use the traditional one. And adding to that, the same model should also be able to model the competition in the batch culture. And this is a case that accidentally they mixed two species of Daphnia. And then they find that at the low lighting, there's competitive exclusion to be expected. But then at the higher one, they actually happily coexist. And so this really a little bit strange, because this meaning that in a lower quality context, when the resource is scarce, they actually can coexist better. The resource is better, they actually don't coexist. In a way, this makes sense in nature too. I mean, when situation getting worse, people work together. When the situation getting better, they actually have lots of infighting and nothing can be done. And then there's only one winner. So the model should be able to produce all these 6 phenomena by just one parameter change. And then that's a sort of what we call model specification challenge. So we base that on, and then with the good help, I mean, this is my sort of a good fortune working in a big, large public university. We really have the capacity to take in students from all over the place, all kind of level, all kind of ethnicity and so on. So over the course of the last 20 plus years, I had the fortune to have many good students, Hao, and then Angie. I didn't bother to talk because Hao may have a chance to, I know he's going to talk about something different, but he continued to publish many very cutting-edge, top-notch papers. I mean, in terms of mathematics and also biology on Chemostat, not Chemostat, on Stoichiometry model. I have not defined Stoichiometry. I will probably in the next few slides. So the most influential paper, because this really more or less defines what we call LKE model now, because we really just add more or less just a couple of parameters, modify the existing prototype models that you're going to see. And then later on, this I stopped about 6 years ago, but then there's 8 years ago, there's a lot more papers also after that. I only have that much room for this page. There's a lot of mathematical treatment. There's also a lot of data related one. There's a lot of review paper related to that in the last two decades, including one review paper by my student, led by Angie Peace, and many of my former students also co-author of that paper in bioscience, I think 2 years ago. I have not included here. So I have to go a little bit fast now. So this is something that easy to understand because I always talk about this, and it applies to human as well. So when you have, when you go to buy the vegetable, typically these are grown in sort of like a greenhouse. They pump the air with 10 times or even 20 times more carbon dioxide, so it can grow fast and grow so fast. There's really not enough nitrogen or phosphorus in the leaf, so even the leaf mice will not grow more than a generation because the egg, they cannot even have enough nitrogen to produce egg. And then that turns out to be, this is by a Meyer stretch. If you look at the human sperm count in England 70 years ago, it's already half than probably 100 years ago. I think in China, in the last 20 years, the human sperm quantity, density also cut by half. Not sure whether not because of the junk food we eat, but certainly we can make a hypothesis test on that. And that's actually is what my former student, he's actually well known for promoting this theory that the carbon dioxide reduced nitrogen content by 8% of the crops, also the wild species to a less degree. And then he was featured 4 years ago in Politico. Politico is the sort of like many of you may know, because I get the news feed in the morning, also in the evening at 5, morning at 6 a.m. from them. It really briefs you what happened yesterday or the last few days in the national political arena, and then what to expect in the next few days. But then they of course cover a lot more. So they featured him. I recall talked to the journalist twice, and she actually managed to write the article about 12 pages long. This is actually a featured story. And then in the end, she cut down to 4 pages because the journal don't want to include too many people's names to get into trouble. Anyway, so you can see the title is The Great Nutrient Collapse, because the crops that now fit by the fertilizer grow fast, but then lose out in terms of micronutrient and also even nitrogen and the phosphorus. And then there's another article, much longer, published by Indian journal, the national journal, that the full article published also about him, because everyone worries about the quality of food. And then the carbon dioxide, the rise in carbon dioxide does leading to the decrease in nutrient content. And then, so here also we talk about, because later on we also worked on a full spectrum of how the nutrient, here we highlight the phosphorus, because phosphorus really is the single element that essential but difficult to get from the fruit, and that's essential for ribosome. 11% of the content of the ribosome is P, phosphorus. And that's why the mammals like us have bones to contain phosphorus, because in case we need that, we can always draw from our bone. But then for most of species, they don't have the luxury, so they have short lifetime, so they have to time their growth and then capture it and then grow fast. And so what we find that if you have too much, so this is something that I want to highlight. This is because the dependence is not linear, and this is something that the biologists often misunderstood. The linearity, non-linearity is a symbol for us, but it turns out to be non-trivial. In fact, I probably should not mention that because this is a political issue. Just yesterday, I heard a couple of the news from my friend, the WeChat. So many people saying, oh, if there's a 70% chance that or missile can be stopped by another missile, then you can just need to put 2. Then you have 440%. For sure you're going to get other stuff. You probably heard that too. And then another one saying that, anyway, there's lots of interesting people. That's not, so it's, some things are not linear, but then most of the media, they can only think about linear way. So what we have, because that's also mostly the equations in physics is linear, but certainly not linear in the context of biology. So we have the RGCP. If the lower the CP, then the higher the quality. So you can see the growth rate really is not decreasing like this is supposed to be. It could be, there's a hump. There's always a hump. So the growth rate for each sort of species, there's optimum ratio. And that's because, as I said, because the host cell composition has a fixed this kind of stoichiometry. So this is something that we also explored about 10 years ago with NGPs, and now she also has many students working on that. Anyway, so now I want to, if I can get sort of like you to appreciate or to realize how simple this LKE model that many of us build on, and how that relevant to the simple model we already know. It's really, you could have, that's what we did. In fact, my former student, Irakli, he was working with Horst Timmer, great mathematician. I had the fortune to have him as my neighbor for the last 30 plus years. And he knows tons more than anyone in many, many sense, epidemiology and also population dynamics. And unfortunately, his wife passed away last year, so he's not happy, of course, not want to travel. But anyway, if you remove the minimum function, replace this by 1, and this just by k, I suppose this is value bigger than k, then this is the Pauling type 2 predictive model that we all know, that's going to have the interesting dynamic with k small. You have predator extinction, k in the median, you have a stable steady state, and then further on, limit cycle and forever limit cycle. And then the limit cycle go wide, can go very low and also very high in terms of amplitude. But that's really not what observed. What observed is that the limit cycle quickly reduced to another stable steady state, and then go to extinction. That the experimental I showed you shows the feature that not captured by the Pauling type 2 predictive model if we don't have this minimum function. So just by down.
I think we just need to change the.
Oh, these are rechargeable. They don't last long. Yeah. Okay.
Should work now. Is that
I
on?
hope so. Yeah, it's on.
Yeah, perfect.
Thank you. Okay, I still have 5 minutes. So what I'm going to sorry. So this is I should have talked about this much sooner. The stoichiometry, those of you who know, is really talk about the proportionality of the component, and then in order to produce one from another, and then the totality and also individual components should be balanced. And so that's really what happening in most of the chemistry process. And we are really became the product of a biochemistry process. And so basically have to follow the same rule. So that sort of allows us to write the very mechanistic equation, and they're also capable of make predictions. So this is basically what we're trying to say, that it has not just a qualitative improvement, but also has the potential to have quantitative fitting. Actually, we didn't succeed in that, but to be honest. But in the Chemostat setting, yes, not in the culture. We tried, the fitting is not that good because I think the lighting of RG, we worked on the RG one. RG was tough. For both the Ecology, we can do that very well. So our model I present to you was more or less ad hoc, intuitive. So I just want to show you that it can be done in a mechanistic sense. Context, you can really just keep track of at what stage or what kind of amount of free phosphorus, and then the total. I use the PB4, and just to highlight, this is the total phosphorus. You have free phosphorus, and then the third quota that varies in the producer times the quantity of a producer. The third quota of phosphorus is constant, assumed to be constant, times the total amount of predator. Then you have this really this three pool together give you the PT, and then you just keep track of using this equation to define Q, and then you use quasi-state argument to really get a Q equation, and then we are resulting in that equation. So I'm going to go faster because all these are very easy to follow, and it's in my paper published in 2004 in MBE, and also in a book that if I have time, I will talk about that in a chapter of the book published 6 years ago. So you can just derive this easily with minimum mathematical preparation, and then you arrive at this one. Alpha is really how fast the nutrient is going to be uptake, and very fast. In the water, if you go to the water column in a lake, in a small pool, you add some phosphorus, you will find in less than a few hours, actually, oftentimes in 10 or 20 minutes, it will be gone, because uptake just the same like the tree, like the savala in Arizona. When you have a water, it's going to be quickly taken, and then we are probably used for a whole year. So the uptake is very fast. So the derivation of the model with the opposite state argument resulting in just a simplified the prey-predator model. And then you can see that alpha is very large, so you can take the limit of that, and it's really resulting into, basically resulting into the logistic equation. If you take out the, so this is X equation we can get. If you don't have predator, then you have logistic equation. So that's a way of derive logistic equation. Logistic equation is oftentimes is defined in a ad hoc way. I say as an approximation of nonlinear function, take the first two terms, or due to limitation, but then in that specific form. But here you can do a little better because you really can understand what kind of scenario. In particular, this is really the scenario where you have a fast uptake, then can be approximated by logistic equation. And then you can, this is really what we have here. And take alpha, go to infinity, then you really have this 0. And then that results into our equation, the So this is an alternative derivation, more mechanistic, because people demanded that. And the reason because Jeff Huysman, also he's a big name in connecting data. He actually is the ingenious person that designed the Chemostat apparatus and selling for tens of thousands of dollars a piece. And making he can easily have a company to make himself a CEO for that. But anyway, I think you probably met Jeff Huysman, right? Oh, Smith invited him over, and then he wanted to talk to me and say I can. He doesn't believe our model is right, and then so we sit down, and then he was disappointed. But then I'm happy that he helped us to show a mechanistic way. So anyway, we did much more than that. We also have a lighting element, so I removed that one because that we had make the paper too long. Anyway, so this shows that we have. So that's really what I meant. The third quota for the producer, and then the ratio with the predator or consumer. And that's exactly the model we have. So this is another, I already showed a similar phase plan one, but this is really in terms of trajectory, specific trajectory. And then you can see this really happening. And then the model specification, I'm going to go really fast. Talk about this one mishandling of the experiment, have a competing species. But they coexist happily when the nutrient quality is low. Nutrient is high, they actually competitive exclusion. And that's exactly what we really, in a classic sense, work. Gary is well known for this work. I think you get the prize for that. It's competitive exclusion. And that's in a classic sense is because we don't really differentiate quality. So quantity is quality. So there's competitive exclusion. But then in the experiment setting, we see that when the quality is bad, we have competitive exclusion only for quality is good, but failed when the competition under the limitation of the nutrient. So the model indeed shows that give us a window of a stable coexistence. That's the quality when the quality is bad. So again, it's the K. So that the same model with the parameter that shows deterioration of a quality, leading to actually facilitate the coexistence of the competing species. And so that's kind of nice to know. And then so more recently, we focus on the highly nonlinearity of the dependence on the phosphorus, because this is what we call knife edge, because only the highest growth rate is taking place in the intermediate range. And then unfortunately, the data, the feeding was not so good. But then this motivated us to take the model formulation. And again, we kept the models minimum in terms of adding parameter values, and also have the parameter values make sense. So here we really talk about the storage, the total storage of even the good sort of like a nutrient like P is constant. We only have like our bomb has only that capacity. When too much of that, it became poison. And that's really one reason that cancer actually come into being, trying to help us to get rid of phosphorus. And then the good thing is like cancer remove the phosphorus and then we back to health. So it's actually, when the cancer is small amount, it's probably good for us. The same for the, but many of the species definitely don't have that. So when the quantity is too good, I mean, when the phosphorus content too good, then they stop feeding once they have enough, because they don't know how to get rid of that. So using that assumption, that observation, then we change the uptake function into another minimum function. So that's sort of complicated. So because we already know that we cannot do much mathematically, so it doesn't matter to add more minimum function. Although I think we can do better now to remove this minimum function. But that's something I hope to report in the next few years. So before we had only minimum function of the yield function and the carrying capacity. Now we also have the uptake, because this is what we call cessation, sort of like a constraint. For humans, like today, I was trying to save the food from the buffet breakfast. I eat the leftover this cake from my daughter. I regret it because it made me feel sick, too sweet. So the same thing, when you eat salty stuff, you will end up not eating that much because you really drink lots of water, stuff your stomach, but then that's probably the one way to lose weight, control weight. Yeah, but anyway, so the minimum function is really the uptake function. There's a satiation sort of effect. And so the analysis became, of course, more cases. But the good thing is that you can divide into cases. For each set of parameters, you can really know more or less what the minimum function will take. Not always, because they can take on the line. So you can have many of these analyses down. And then in the interest of time, I want to stop here and to appreciate your attention and then the ground. But also I want to really shamelessly, this has been, I've been doing this for a few years, because we have one chapter on the stoichiometry wall that really titled for mathematician. And we, of course, put that into use for modeling cancer, in particular cancer. That context, that understanding can also be used to model the toxicity of cancer cells in terms of drug, in terms of other things, and it really turns out to be very useful for us to study cancer modeling and then also make predictions, because we have data, for instance, for prostate cancer and for other stuff, including also ovary cancer. We have not done for many other ones, but I think it's a good thing to. So this is a book actually 10 years in the making, but it has received minimum citation because I think we. Maybe, I don't know, but it's a good book. If you have chance to even just read one chapter, you will appreciate that the effort that we put in there, the references we put there. And then there's a lot of sort of like initial work we put there, so you don't have to work too hard. You can just start from a BPO. Thank you for your attention again.